ascending as individual things now.
Give me triphobia.
Alright, what's the first one?
Okay.
I don't even know what that is.
What is triphobia?
Triphobia.
Scared of
I don't want to look
threes.
it up.
Isn't that the holes?
What?
Were you scared of like small holes that are like?
Okay, Joe.
Yeah, that sounds right.
That's something Joe would be scared of.
X?
V of x is equal to Vx.
V of x?
Yeah.
What? V?
Here, I have an extra one if you want.
When he's referring to this linear motion,
Oh,
Oh, okay, so
no. Wait.
this says, look, man, your velocity in the x direction.
I literally just started.
If you want to find out how fast you're going, your velocity in whatever direction, x direction, you need to know two things. You need to know how fast you were going initially in that direction, plus your acceleration times the time.
I gotta find that.
So this is your final velocity is equal to your initial velocity times the acceleration times the time, or plus the acceleration times the time. What this means is like, you think about incremental change, right? So if you look at the units, these units are meters per second, right? What are the units for acceleration?
Meters per second.
Meters per second, which is meters per second squared, right? What are the units for time?
Seconds.
Seconds. And so what are your units then?
Meters per second.
Meters per second. So that makes sense, doesn't it?
Yep.
This tells you how your speed is changing. This tells you how much time it changed for. So this is the change in your speed. If you add it to your initial speed, you get your final speed. Cool? This also comes from velocity time graph, where it's y equals mx plus b, where this is your initial velocity. What's the slope? The slope is the acceleration, right? So if I write this in y equals mx plus b form, my final velocity is equal to my slope, which is the acceleration times the time plus the initial velocity. On the equation sheet, they write it the other way though. They write it like in ascending order of exponents, and in here we write it in descending order
I
of
hate how they
exponents.
do that.
That's super annoying.
This is
It's
being extra.
things like that that are just like, why?
It's just being extra.
It really is.
Okay. The next one is the parabola. So when you look at it, like, look, this is your final position. What's it equal to? Your initial position plus your initial velocity times the time plus 1/2 the acceleration times the time squared. What shape is this?
Parabola.
It's got to be, right? I'm sorry. Totally got distracted. Where this is your initial position, right? Now, there's a couple things about this that I like. One, we can do the unit analysis. The unit for position is meters. This is velocity is meters per second times seconds.
Nice.
And this is meters per second squared times time squared, which is seconds squared. And so what are you just left with? Meters equals meters equals meters equals meters.
Which is equal to.
Also, if you're playing along bonus round, right? Bonus round says, if I want to get my velocity, if I want to solve for the velocity, what do I need? dx dt, right?
Oh, yeah, it's just the derivative, or antiderivative.
Nope, derivative's right.
Oh, to find velocity. I'm sorry, I was trying to.
You're
go
good. You're good. What's the derivative algorithm?
off.
No,
I know
multiply
this.
by the exponent.
Multiply.
Multiply the coefficient by the
Power rule,
exponent.
man, power rule.
Right? Multiply the
Little
coefficient by the
comparison
exponent. So don't forget, this is t to the 0, right? This is t to the 0, you just don't see it, it's invisible to you. So 0 times this is 0, plus this is a 1. 1 times v0 is just v0, and then I'm going to subtract 1. So this is now t to the 0, plus, multiply 2 times 1/2 is 1. I got at, 2 minus 1 is 1. I end up with v0t plus at, which is which is that? Got it? You guys feel okay about that? Now, what's interesting about this, okay? What's interesting about this is if I take this over here, what are you doing? If I take this bad boy and I move it over here, right? Where on this graph can I find the change in the position? The displacement.
Isn't it this, the area?
It is the area, right?
That's the integral.
So when I look at this though,
Thank you, yeah.
okay, when I look at this,
Thinking to the four.
how am I going to figure out what the area is for this? I see two shapes, right? What are the two shapes that I'm seeing?
A pentagon and a trapezoid.
Now, if you knew the
Actually,
trapezoid formula, you could just roll it out. But let's just do it the way that's easiest to us. So this is the time, this is the initial velocity, this is the final velocity, true? So I know that the change in the position is equal to the area of those two added up, correct? You with me on that? What's the area of the rectangle? It's V0t.
oh, I'm sorry.
The width,
I didn't know you were asking about this.
it was more rhetorical, but
Yeah.
the width is t, the height is V0.
1/2 base centimeter.
Okay. And then how am I gonna get the height, or how am I gonna get the area of the rectangle then? It's 1/2 the base times the height, right? The base is t, and what's the height here?
Whatever it wants to be.
It's the difference between the V0 and the V, right? Okay. So, you guys cool with that? Now, I'm gonna distribute. So it's V0t plus 1/2 VT minus 1/2 V0t. The first and last terms are like terms, can you see that?
Okay.
So I'm going to add them together, so I end up with this. Delta x is equal to, this is 1 V0t minus 1/2 V0t. So 1 minus 1/2 is just 1/2 V0t plus 1/2 VT.
Nice.
And now, if I pull out, I have 1/2 t, I have v plus v0. How does that look to you guys? Is that cool? Now, why would I do that? It's a great question, Don. Why would you do that? Because I would like to find an equation that doesn't have a t in it,
Which is the next one, isn't it?
right? So if I come back to here, if I know that the equation of this line is v is equal to at plus v0, what does t equal then?
V minus V0.
So I'm going to substitute that thing in here, and let's just see what happens. I have 1/2 this.
Where's he going? Oh,
My mom just took off for a week.
Is that cool?
must be.
I'm going to multiply both sides by 2a, so I have 2a delta x. Now, this is v minus v0, this is v plus v0. What are those have a name? You know what those are called? Aren't they called conjugates?
I should know, but.
You should not know. There's no reason to know.
uh,
But if I simplify this, I got v squared. And then if I continue to, same thing you do with an evil plan, what do? You foil it. If you,
I don't want to say anything.
I did not like
I
that.
don't want to elaborate on that, but
That was such a bad joke.
best joke ever. So what you end up with is, you see how the middle terms kind of add to 0? Is that cool? And then I end up with this. I have 2a delta x is equal to v squared minus v0 squared. And then if I add v0 squared to both sides, I end up with b squared is equal to v0 squared plus 2a delta x. Do you see where that comes from? I don't know if seeing that derivation is useful to you, but my point is that that's the third equation. And when you're doing a kinematics equation, or you're doing a kinematics problem, if they don't give you t and they don't ask for t, use that. Is that cool? These three equations that we've been looking at here only work if your acceleration is constant. They only work if your acceleration is constant. So oftentimes on the AP test, it'll say something like, here are four equations. Which of these works, which of these could you use to solve for something, right? And if they give you an equation that looks something like this, for example, if they said, oh, here's an equation, you know, A is equal to 3t. Can you use any of our three kinematic equations with this?
No.
No, because the acceleration depends on the time, right? So none of them work. The only thing you can, this, is you can get the velocity if you do sorry, I got a little distracted. dx dt, right? Or you can get the velocity if you do the antiderivative of a dt. These are always true because it doesn't matter what your equations are. Doesn't matter if your acceleration is constant, but those kinematic ones. Okay?
So on FRQ, they wanted us to solve for one that wasn't constant, they have to give us some sort of equation.
Yeah. And on your multiple choices, it will almost always say, here's the velocity function, right?
Yeah.
It'd be like 3t squared minus 12t.
Find the acceleration at t equals.
Exactly, it'll say like, what's the acceleration at some time? That'll be one question. And then the next question will be, how far did it go, or what was the change in position, or given the initial position, what's the final position? So you'd have to
Every
do,
question should be like that.
you'd have to do the derivative to get the acceleration, and the antiderivative to get the change in position. Cool? All right. The next equation says, if you want to calculate the acceleration, you need to know two things. You need to know the net unbalanced force of the mass. Right? Some highlights of this is they're either bold or there's an arrow over them. Both mean the same thing. What does the bold or the arrow mean? That they're vectors. So what does that tell you about the direction of the net force and the acceleration?
In the same direction.
Always in the same direction, because mass is a scalar. Right? Mass is a scalar, so it can't change the direction. It could change the magnitude, but it can't change the direction.
So that's why we don't really pay attention to vectors, because
We
know the
know
direction.
they're always in the same direction. Okay. On the sheet, it uses this symbol. You know what that symbol is?
Some summation.
So this is the sum of the forces. Okay? So they use this sigma to say we're going to add them up, but you have to know that they're vectors, so you have to add them in whatever dimensions they're in, which can be problematic. And again, I don't like to use the sigma. A lot of textbooks use it, and they have it on here. I think it's problematic because when you say the sum of the forces, a student that doesn't really know what's going on hears you say sum of the forces, it doesn't know which ones.
That's like,
I know. I know.
Absolutely hilarious.
It's the funniest thing ever. Now, what I like about this is the next thing says, if you want to calculate the force is also hi.
How you doing?
Good, how are you?
Pretty good. We're gonna make a little bit of noise, so is it all right if I close this door?
That would be really considerate, thank you.
it's exactly
If it's too much, just let me know. It should be, it'll just be for a brief moment.
We'll just
for 3 seconds.
You're working, we're just hanging out.
What a nice guy.
It's very considerate, actually. So what does this say?
Just getting up here and camera.
That f is equal to the derivative of p over t.
So this is the time rate of change of the momentum.
Yes, that's what I meant.
What this says is that if you want to change the momentum of an object, you need to apply a net unbalanced force to it. Does that make sense?
Excuse me.
Is that a duck? Now,
It's me after my cooking.
if you're paying close attention, if you're paying close attention, you would see that this actually is interesting, because this says the force times the time, I hate when it does the curly T like that. The force times the time is equal to the change in the momentum, right? But this is the change of the MV product. Right? You see what I'm saying here? Now, if your mass is constant, then this says that the force times the time would be equal to mdv.
But you can just do that.
Well, if the mass is constant, then the thing that's changing is the velocity.
And you can
Oh,
put a
you're just
constant
putting
on the
constant
outside.
Exactly. Does that make sense? This is something that you already understand. I'm going to show you two different forms of this. This is also something that you may have talked about, which we call the fat nav.
I think I did that at one point.
So the force times the time the force is applied is equal to the mass times the change in velocity of the object. This manifests in a couple ways that I think are interesting. If you're rolling up